Okay, so at high level, here is what we are going to do. We are going to build an online store like any shopping website you have used, and we are going to understand every important piece that makes it work. And we will do it in the exact order things actually happen. You open the site and we follow the request, one concept at a time, all the way down to the database and back. And my goal is simple. By the end of this, you should understand every core system design concept that comes up in the interviews: DNS, load balancers, caching, databases, queues, microservices, all of it. Not just what the word means, but how it actually works and why it exists. So, this is not a quick tour. We will properly teach each concept, and then each time I will show you where it sits in our store. So, the whole thing stays connected in your head. And one thing to know upfront, this is a four-part series because there is genuinely a lot to cover, and I would rather teach it properly than rush it. This part 1 is about how a request travels the internet, how it even reaches a server. So let's start at the very beginning. You open your browser, you type the store address, and you press enter. The page loads. Simple, right? But how? What actually happened? Let's find out. So, the very first concept before anything else, DNS. And this one comes up in almost every interview. So, let's understand it properly. DNS stands for Domain Name System, and at high level, it is the phone book of the internet. Here is the problem it solves. You typed a name, let's say shop.com, but computers do not find each other by name. They find each other by a number called an IP address, something like 52.94.236.248. So, before your browser can talk to the store, that name has to become that number. That conversion, name to number, is the whole job of DNS. Now, how does it do it? Because this is the part interviews actually ask about. It is not one single lookup, it is a chain of them. When you press enter, your browser first checks its own memory. Have I looked up this name recently? If not, it asks a recursive resolver. This is a server, usually run by your internet provider, whose whole job is to go and find the answer for you. And if the resolver also does not have it, it walks down what we call the DNS hierarchy, which has three levels. First, it asks a root server who handles .com names. The root points it to a TLD server. TLD means top level domain. The .com, the .org part. The TLD server then points it to the authoritative name server. That is the server that actually holds the real IP address for shop.com. And that one finally returns the number. Now, that sounds like a lot of steps, right? And it would be slow if it happened every single time. So, here is the important part. Everyone along that chain caches the answer, meaning they store it for some time and reuse it. And how long they keep it is decided by a value called TTL, time to live. So, the second person who looks up shop.com does not repeat the whole walk. They get the answer instantly from a cache. That is why DNS feels instant, even though a full lookup touches several servers. Two more things worth knowing because interviews bring them up. One, the answer is not always the same IP. Big websites use something called GeoDNS, which returns a different server depending on where you are in the world. So, a user in India gets a server in India, and a user in the US gets one there. That is actually load balancing happening right at the DNS level. And two, DNS has different record types. An A record maps a name to an IPv4 address. A C name is an alias, one name pointing to another name. You will hear A record and C name in the interviews. Now you know what they are. So that is DNS end to end. And in our store, DNS is simply the step that took the address you typed and turned it into an actual server your browser needs to connect to. Now, your browser has the address, but it cannot just start sending your data across the open internet. It needs a proper, secure connection first, and that is our next concept. Okay, so your browser has the IP address. Now it has to open a connection to that server. And the way almost all web traffic does this is with a protocol called TCP. And a protocol at high level is just an agreed set of rules for how two computers talk to each other. TCP it stands for Transmission Control Protocol. So, what does TCP give us? One word, reliability. The internet underneath is not reliable. Packets of data can get lost, or arrive out of order, or arrive twice. TCP sits on top of that mess and gives you a clean, reliable, ordered stream. Every byte you send arrives exactly once in the right order. And it starts with something called the three-way handshake, and interviews love this. Before any real data is sent, the two sides say hello in three steps. Your browser sends a SYN, basically I want to talk. The server replies SYN ACK. Okay, I heard you and I want to talk as well. And your browser sends back an ACK. Great, let's go. Three messages and now the connection is open. And after that, TCP keeps track of everything. If a packet gets lost, it notices and sends it again. If packets arrive out of order, it puts them back in order. And quick contrast interviews like there is another protocol called UDP, which does none of this. No handshake, no resending, no ordering. It just sends the data and hopes it arrives. And that sounds worse, but it is actually faster. So it is used where speeds matter more than perfection, like video calls or live streaming or online games, where an old packet is useless anyway. Okay, so now we have a reliable connection, but there is still a big problem. Right now, everything traveling on this connection is in the open. Anyone in between on the same network or at your provider can read it. Your password, your card number, everything. So we need to encrypt it, meaning scramble it, so that only the two ends can read it, and anyone in the middle just sees nonsense. And that is the job of TLS, Transport Layer Security. And by the way, that is the entire difference between HTTP and HTTPS. HTTPS is just HTTP running inside TLS. The S is the security. Now, how does TLS actually make it secure? There are two ideas here and both come up in interviews. The first is encryption keys, and there are two kinds. Symmetric encryption uses one shared secret key to both scramble and unscramble the data. It is fast, but both sides need the same secret, and that raises the hard question: how do you agree on a secret over an open line where everyone in the middle is listening? And the clever answer is a method called Diffie-Hellman, which lets the two sides agree on a shared secret key without ever actually sending that key across the wire. This uses what is called asymmetric cryptography, meaning a pair of keys rather than one. So the flow is use this method once at the start to agree on a shared symmetric key and then switch to the fast symmetric key for the rest of the conversation. So you get both a safe way to set up the key and fast encryption after. And one nice property worth naming in an interview, because a fresh key is created each time and never sent across. Even someone who records the whole session cannot go back and decrypt it later. This is called forward secrecy. And there is a second problem TLS solves. How do you know the server is really the store and not an imposter pretending to be it? And the answer is a certificate. When you connect, the server shows a certificate that says, I am really shop.com, and it is signed by a trusted third party called a certificate authority, a CA. And your browser already trusts a list of these authorities. So if the certificate checks out, your browser knows it is really talking to the store. That is the little padlock you see in the address bar. So the certificate job is identity, and the Diffie-Hellman step job is the shared key, two separate jobs. And if an interviewer asks you to walk the TLS handshake at high level, it is just this: a browser says hello, the server sends its certificate, the two sides agree on the shared key, and then the encrypted conversation begins. That's it. So, putting it together, TCP gives us a reliable connection and TLS makes it private and verified. In our store, this is the step that happened silently the moment the page started loading. A secure pipe was built between your browser and the server, and now that pipe is ready. Your browser can finally send its actual request, and the language it uses to do that is our next concept. Okay, the secure connection is open. Now your browser sends its actual request and the language it speaks is HTTP, Hypertext Transfer Protocol. And HTTP is beautifully simple. It is a request and a response. Your browser sends a request, give me this product page, and the server sends back a response, the data. That is the whole model. Now, let's look at what is inside a request because interviews ask this. A request has a few parts. It has a method which says what you want to do. It has a path which says what you want, like slash product slash 42. It has headers which are extra information about the request, like who you are, what format you want back, and sometimes a body, the actual data you are sending. For example, when you submit a form, the methods are worth memorizing. Get means read something, just fetch it. Post means create something new, like placing an order. Put means update something. And delete means remove something. Read, create, update, delete. And the response comes back with a status code, a three digit number that tells you what happened. And these are grouped into families, which is the useful part. Anything in the 200s means success. 200 okay, it worked. The 300s mean redirection. Go look over there instead. The 400s mean you made a mistake. Like 404 not found, the page does not exist, or 403 forbidden, you are not allowed. And the 500s mean the server made a mistake, like 500 internal server error, something broke on their side. So 400s are your fault, 500s are their fault. That single line is worth a lot in an interview. And one more property, which will matter a lot later. HTTP is stateless. That means each request stands completely on its own. The server does not automatically remember your previous request. Every time you ask for something, it is like the server is meeting you for the first time. Now, that raises an obvious question. If the server does not remember you, then how does it know you are logged in across many pages? Hold that question. We have a whole concept for it later. For now, just remember, plain HTTP has no memory. And finally, you will hear two more words a lot: API and REST. An API, application programming interface, is just the interface one program uses to talk to another. It is the set of requests our server agrees to accept, and REST is the most common style of designing that API in a clean, predictable way. You have resources like products or orders, and you use those standard methods on them. So, get slash products reads the list, post slash orders creates an order. Two practical things interviews ask about a real API: pagination, meaning when a list is huge, you return it in small pages instead of all at once, and versioning, so you can change the API later without breaking apps that already use the old one. And you will hear a lot of alternatives to REST like GraphQL and gRPC. Just know they exist as other ways to build an API. And one last thing, HTTP is request and response, one round trip. For things that need to be live, like a chat or live notifications, you use a different kind of tool called a WebSocket, which keeps the connection open both ways. So the server can push updates to you. Just know that it exists. So, HTTP is how your browser and the server actually talk. In our store, this is the request that page went out asking for the product page. Now, that request has arrived at the server. So, what is a server and what does it do with your request? That is next. Okay, the request arrived at the server, but let's be precise about what that even means because client and server are the two most basic words in all of this. A client is the thing that asks your browser, your phone app. A server is a program running on a computer somewhere whose job is to answer those requests. That's it. Client asks, server answers, and one machine can serve millions of clients. Now, inside the server is usually not one thing, it is two, and the interviews sometimes check this. There is a web server, software like Nginx, and its job is to receive the raw request, handle the connection, and serve simple files quickly. And behind it, there is an application server, which is where your actual code runs, your business logic. So, when the request comes in for place an order, the web server receives it and passes it to the application server, which runs the real logic. Check the item, calculate the price, save the order. So, what does the application server actually do with a request? At high level, a few steps every time. It reads the request and figures out what you want. It may check who you are. It runs the logic. Very often, it needs data. So, it talks to a database, which is our next big concept. And then it builds a response and sends it back. And one small piece you will hear about sitting right at the front, a reverse proxy. Think of it as a receptionist for your servers. Every request hits it first, and it can handle the secure connection and decide which server to forward the request to. We will come back to it properly when we scale up. So the server received your request and now it needs the actual product data, the price, the stock, the description, and that data lives in a database. And that how data is stored and how we make it fast is exactly what the next part is about. So that wraps up part 1. We have followed a single request all the way from your browser through DNS, a secure connection, and HTTP to the server. In part 2, we open up the database and everything that makes data fast. If this was useful, subscribe and I will see you there.